Okay, great. So it's a great pleasure to have Mukund Rangamani here, and he's going to tell us about spectral function asymptotics and the practice.
Thanks. It's great to be back here. So I've decided to talk about a recent paper with a former student at Davis who worked with Veronica Hevejia, who is now at Beijing. And I'll say something about other related work that appeared in the last year, primarily, but also stuff that by now is prehistory dating back 20 years. And so the short paper that we put out in December, and hopefully a long paper that will come out this week. The question that motivated us is the following. How does one decode geometry or signatures of geometry from field theory data in a holography? Okay, so this is not a question that we're asking for the first time. It's a question that's been asked ever since the ADS CFT correspondence. And we have, over the years, built up a repertoire of various tools that probe various aspects of geometry. Okay? And something would be that early days people started studying correlation functions, which is primarily what I will focus on. And then the more fashionable thing is to look at entanglement entropy of subregions. And you can think of this as part of this general bulk reconstruction program.
Can I even ask you a question at this stage?
Yes.
Isn't the thinking that after all the bulk description is hugely gauge redundant, therefore, I mean, what does it exactly mean? All the gauge invariant stuff is, of course, just the operators and their correlations. But
sure.
Of course, still, did you mean in some quite precise way, like the radial direction is some energy, whatever, make all those notions precise?
That could be one theme, which is not be what I want to do right now. But one question is, there are certain bulk features that are covariant, which don't care about your particular coordinatization, and those would at least benefit from having sharp diagnostics in the field theory. And my goal at least is to say, suppose you have the sharp diagnostic in the limit where a classical bulk geometry is reliable, so large N, strong coupling. When you then are able to solve the field theory at finite and intermediate coupling, can you see how the sharp diagnostics help you decode the geometric features? Okay, I think that question is robust. It does not suffer from the ambiguity you're talking about, and therefore it indeed does behoove us to write down the data directly in terms of gauge invariant observers of the field theory. Okay. So that's going to be the question, and in particular, the one thing I will really focus on today is just the black hole singularity. Namely, if I told you, okay, look, there's a thermal state of the field theory, it's dual to some black hole. That classical black hole has a curvature singularity. Where do you go and look to see what that curvature singularity is? And if you are at finite and finite coupling, it's a singularity result. So without knowing the diagnostic, you're not going to have that resolution.
Thank you.
So right now it's just going to be the diagnostic. I think there are prospects, and I'll highlight them as we go along, of how one might be able to go about doing this. Good. So instead of bulk reconstruction, today the question is about identifying signatures of space-like singularity inside, let's say, Schwarzschild-like black holes. Okay. I could say something about other black holes, but for now let me just focus on this particular example. I'll come back to this question and explain what was done more than 20 years ago, but I'll highlight one statement that was made back then, namely 2-point functions of gauge invariant operators in quotes know, by which I mean they carry some information about the singularity. So, I'll therefore start by focusing on studying the 2-point function of some operators, let's say at finite temperature, and we will strictly work at large n. Some conventions before I get started. So let me, I will end up, I'll say some things in position space first, but then I'll switch to momentum space in a second. I will come to which particular correlator. Right now this is just some Whiteman function in let's say in Lorentz signature at finite temperature, and they're inserted as written on the same side. But I will discuss the connection to the two-sided correlator in a thermophile double. I will discuss the connection to the retarded correlator, etc., etc.
And is it going to be restricted to the thermal state, like the singularity is in both dynamical states and so on?
Good. So for now, I will only talk about the equilibrium Hartle-Hawking state. I will not discuss non-equilibrium dynamically evolving thermal states. It's an interesting question how to generalize this discussion.
This relies a lot on the analytic structure and so on.
Exactly. Exactly.
It's never been clear to me how it works.
Yes. Yes. I completely agree. Although I think that analytic structure is still powerful enough that eventually there's some statement that one could make, even at, let's say, at late times in a collapsing situation. But I think you'll be right in saying nobody's ever done it. Good. So that's the context. So now let me flesh out what we want to do. So let me talk about this particular spectral function, which is the object of interest. So this is going to be related to the retired Green's function. So let me call the retired Green's function and switch to momentum space for now. And let's call it, let's just stick to position space. So this is the expectation value of the commutator with some theta function. In time, and the spectral function is nothing but its let's say in frequency space it's given related to the retired Green's function by taking real or imaginary part depending on your conventions, but I've chosen to write it this way. And then the last subject is the one that Pratik asked about, which is the two-sided correlator. So and this in frequency space is related to the spectral function after stripping off the Bose-Einstein factor. Okay, so if I can control the spectral function, I can control the two-sided correlator, because strictly speaking, there's only one piece of information in all of these things. They're all related to each other.
So
So is the spectral function what you get by inserting a complete set of states in the Whiteman function?
Yeah, it's a thing that you should think of as the sort of capturing the actual density of states in the thermal system.
So it's like the Lehmann decomposition.
It's like the Lehmann decomposition of yeah.
That's the Whiteman.
That's the Whiteman function.
You just put it
In this two-sided collimator, so C omega is just the Fourier transform?
It's just there's ordinary there's the Fourier transform, direct Fourier transform. Okay. So there's some statements one can make about these correlators, and we can say something about the Richard-Green's function. So the Richard-Green's function.
Sorry, just for
Yes.
orientation, what would the spectral function equal for a free scale if you have it? If it's not
Not on top of my head. So this Richard-Green's function in frequency space is supposed to be meromorphic and have poles which are related to quasi-normal modes in the bulk. And if you translate this statement to this two-sided correlator, then the statement about the two-sided correlator can be made. I'll switch between position space and frequency space back and forth at various times, and I'll say some things about singularities in both the time domain and in frequency domain. Okay. They're related, but it's interesting to sort of keep track of both at the same time. So of course, given that these are singularities of the Richard-Green's function, there are also similarly singularities of the spectral function. And the second statement is that the two-sided correlator is analytic inside this fundamental thermal strip which runs between imaginary time minus beta over 2 to imaginary time beta over 2. Okay. This will be important for some part of the discussion. In particular, when I talk about using the OPE to say something about the spectral function, it will be important that everything is analytic inside this strip. The OPE will give you enough information about the correlator there inside the strip. Okay. However, because you're not guaranteed analyticity outside the strip, the OPE will give you OPE singularities and it will give you branch cuts outside the strip. And the branch cuts will sort of sit at the edge of the strip.
Sorry, Mukund, I'll ask very stupid.
Yeah.
This analyticity, what I understand is that your density matrix has an e to the power minus beta h.
Correct.
So now if you try to evolve with the wrong sign Euclidean time with more than time t, more than time beta, then you'll be in trouble.
Yes.
So the width of the strip I understand.
Yeah.
How do you get the position?
Position of the strip? Because this guy is symmetric, right? This guy is symmetric it's been pushed one I beta over 2. Otherwise you would have been right, it's sort of between, depending on which one you look at, it's between 0 and minus beta or 0 and beta.
But just let me ask again, there's no real symmetry between positive Euclidean evolution and negative Euclidean evolution. Because one of them,
Yes.
e to the power minus beta h,
Yes,
picks out one sign.
it does.
So somehow, very vaguely, I would have thought that
One sign is
0 and
The correlator is periodic in beta, right?
Right.
And in order to have any causal singularities, the two operators have to be on the same side. Right? So shifting by beta by 2 is like taking this operator to the
Other side, right, exactly.
Yeah.
Yeah.
Those branch cuts are like causal branch cuts. Right?
Yeah, the branch cuts are precisely.
One.
So if you were looking at one-sided correlation, then what you said is correct. The branch cuts would be at 0 and
Yeah.
but he's looking at
He's looking at the two-sided. Now I get it.
Yeah.
So sorry, why is it that going from 0 to beta, whatever is like moving to the other side, suddenly just
It's imaginary. It's moving on the imaginary. It's moving on the thermal circle.
so sorry, but moving on the other side of the two-sided geometry. Yes.
Yeah.
that's correct.
And why is it? You go from 0 to 2 pi, you come back in the trace.
Beta would be coming back, but beta
Half.
by 2 would be going to
Halfway.
Oh, you mean going up from below?
No.
Either up or down. The correlator is periodic.
Okay.
This rho omega cube is that 0 at omega equal to?
Sorry.
This rho omega cube.
It will have a 0 to take care of the things.
And the start feature of
No, this statement is generic. This statement is a generic statement about, these are general statement about thermal field theory.
So can you say why these are the causal singularities? Because when one is on one side and the other is on the other side, in general they will not be.
And that's why this.
No, but they will be causal singularities in the return Green's function, and then those branch cuts will propagate in here, and then the Fourier transforms will have those cuts. Okay, so if you're at fixed position, if x is fixed and different from the coincident limit, if you fix one x, then you can use the periodicity that Onkar mentioned to extend this function into the full complex time plane, and these cuts will just periodically repeat themselves. Okay?
Sorry, one more. Now, your retarded correlator has these poles down there, but
Yes.
the spectral whatever, this thing will also have poles upstairs.
This guy will have poles upstairs as well. Yes, exactly. Yes, because it's two-sided, right? So now it's not just purely retarded. It has some admixture of the advanced, so it will have poles everywhere. Yeah.
And this gap for the branch cut is controlled by x.
Gap is controlled by x. It's basically at t equals x. It's where it's basically light cone singularity is translated onto this space.
So I didn't understand why you said that x variable to be the same in this way. Is that needed or is that just a choice?
It's a choice. We could choose this to be 0, for example. But I want the positions fixed, let's say.
Yeah.
Okay. Keep the positions fixed, because what I will discuss later is what happens at special momenta, or if I smear this over some range of x's. Okay.
But if you smear, then you definitely need x and y.
Exactly. Yeah. Well, I could smear by starting in the Fourier domain and doing some Fourier smearing. Okay. But anyway, the point is that if I fix this correlator, then the analytic structure from the strip can be inherited to tell me what's happening everywhere. So I can extend this correlator everywhere. If I start smearing this correlator either in X or by going to momentum space, and if I either do finite momentum or if I do some kind of spatial averaging, which is sort of related, then I could start having singularities in this complex time. Okay? And this will be important because one of these things is what we will argue knows something about the black hole singularity.
Say again this last point.
1 second, there was a question.
Yeah, that was the question. If you have smeared operators, then how do you smear the light cone singularity?
So the light cone singularities will sort of, they'll stay, but in addition, outside the strip, I will get additional singularities.
Sorry, why would they stay? Because you're smearing it.
But I'm smearing it, but let's say you will get some singularities at which are, so I will try to distinguish what singularities you get from the light cone, where they come from, because they will be visible in the OPE expansion. Okay, so we can decide where those come from once and for all, but there could be additional singularities because of smearing which have to lie outside the strip because they're guaranteed analyticity inside the strip. Okay, so that's going to be the focus of what I'm going to do. Sandeep.
No, so smearing gives rise to additional singularities.
Smearing will give rise to additional singularities.
Which depend on how you smear.
It will depend on how I smear. So for example, if you ask the question, what are the singularities of the Fourier transform of the momentum space correlator at zero momentum. So for example, look at this function. And then Fourier transform it back to time. Okay.
So
Good.
that
You make
CT of Q equals 0.
CT of Q equals 0. So that's smeared in position. It's in fact completely smeared in position.
Yeah.
But that will have singularities outside the strip. It will have images, thermal images, but there will be special loci, none in the strip.
But if it's periodic with beta, then
You're only guaranteed something here. You're trying to take a function that's analytic here with potential singularity on the edge of the strip and continue it outside. You're not guaranteed anything outside.
but this overall function isn't periodic.
So you will get images which are periodic, but the singularities will stay here and here and here. I'll write a formula later and you'll see what the periodicity is.
I'm confused because the image of that under shift by minus beta comes into the strip.
But but you're not allowed to have any. So the smearing breaks that structure.
Okay.
Yeah. The smearing has to break that structure. But you're allowed to have things outside the moment you smear.
I thought the periodicity was just out of the trace, right? The Fahrenheit temperature.
Yeah.
So then if you smear it in X, what is that?
I'm not smearing in time.
Maybe the statement is that you can always make a periodic thing.
Yeah, but
that will not be in the analytical.
of the physical answer. What's on the strip?
Right.
Yeah.
Of course, it can be periodic, but could have a
Yeah.
periodic like this.
Yeah. I mean, you're not. I mean, the question is there's no unique analytic continuation once you have that information because all you're guaranteed is stuff.
Meaning you can always take what's on the strip and just repeat.
Repeat it. Yes, that will be periodic, but that's not
By construction.
by construction.
But it may not be the analytic continuation
of this function.
Okay.
Yeah.
So the analytic property that's right.
Yeah.
Maybe that's.
Yeah. Exactly.
I didn't understand this point. What does it mean? I mean, you can, but it is, I mean, when you identify these two boundaries, it is going to be continuous across it, right?
It will be but there can be singularities on the edge of the boundary, right?
No, but you, in order to analytically continue, you just need one path. You don't need you need the full thing to be open, right? As long as you find some narrow region through which you can go,
Yeah.
you can analytically continue.
So that is true, but I think, but the question is what is the actual analytic continuation of the function?
But why is it different from, if the function were periodic, why would it be different from that periodic function?
Because I think that's not the physical answer. I think the periodic function is not the physical answer.
So periodicity would be broken by the smear?
Yes.
But that's what you guys were saying, right? I mean, if you smear on X, why is it the periodicity in Euclidean times get broken?
But now that I understand the comment, if you analytically continue with something non-periodic, doesn't it raise the question, what is the physical significance of this analytic continuation?
Yes.
Because all objects defined as traces, etc., would be periodic.
All objects defined as traces would be periodic. I agree. Yeah. Let me come back to that question. Okay, so let me, given that motivation and given that I will eventually try to argue that singularities out here are going to be related to the black hole singularity, let me say some statements that you can check, that we can motivate by just studying the, let's say, the spectral function by starting from the Euclidean correlator and analytically continuing to positions to Lorentz signature, and using the Euclidean OPE to make statements about this analytic continuation.
So will this analytic continuation be some Schwinger-Keldysh correlation?
This is a Schwinger-Keldysh correlator.
So it will go up. And
This guy,
Yeah.
this guy is not a Schwinger. C is not a CT is not.
But suppose C is some contour, right?
C is this contour.
Perfect. Now, suppose I want to get to beyond the analytic region of C.
Yeah.
is that effectively changing, is there a physical contour
That will get that?
access that? I mean, is there a physical question that will access that, or is that mathematical?
The domain is a cylinder, right? What does it mean going away from the strip? This is just you are unfolding it. You never ever you are breaking the periodicity of this function. So why should I not just think of this as a function of a cylinder? What does it mean to go away? And
Well, you take correlation functions of in the Lorentzian space of a field theory, you access many different sheets.
yeah, but here the domain is a cylinder. This is to be thought of as glued up.
No,
But it's cylinder of sin theta.
Yeah.
So then it would be periodic.
That's what I'm saying.
let me write some formulas in a while. Let's come back to this question.
Apparently there's a way to analytically compute without the cylinder.
That's what he's getting at. But if it's an analytic configuration, there will be something you can do to get.
Yes, I agree with that, but my confusion is that I don't know how to get it directly from in position space. I'm going to get it from momentum space, and you will see immediately in momentum space why there's a problem.
Roughly, should I think of it as like trying to go in the backward and forward when it's cluster, like analytically continuing the cluster?
Yes. That's essentially what's going to happen,
Right.
but it's not. But that connection is a bit sort of not straightforward. Yes.
Yeah.
I don't know, it was just like, I was saying that in the black hole diagram, if you want to go from region 1 to region whatever, the upper triangle, you do a similar analytic
Okay. So let me make a statement from the OPE. Okay. And I want to tell you what the spectral function looks like. So the spectral function,
Is it that these two different notions are coming from the fact that you can choose a path which is either going through the passing through the cut or not passing through the cut? That's how you are getting two types.
Also, sorry, you said that the cut started at this thing that depended on x, right?
yes,
So if x was 0, then the cut is the whole thing.
yes,
And since you're doing this q equals 0, you're integrating over all x.
exactly,
So there's basically a cut everywhere.
everywhere, yeah.
So you just cannot add.
Yeah. The function doesn't, I mean, the problem is you have a domain boundary, right? So the analyticity.
It's a little bit, eta function
Yeah, across the unit disk.
across unit disk.
Yes,
right?
yes.
Upper half plane.
Upper half plane,
That way.
yeah.
It's completely analytic in the upper half plane.
Yes.
Just you cannot analytically get it.
Yeah.
Unless with some you can analytically
Yeah.
get it somehow.
So the many ways to do this. This was done in a few years ago by various people. I can give you references later. But the spectral function in frequency space, if you just look at OPE, it's supported in time-like for time-like frequencies. Okay, I'll write it schematically like this. The spectral function looks as follows. It has support in frequency space only for omega squared bigger than k squared, so in the time-like region. It has a piece that you can recognize as sort of the vacuum piece. There are perturbative corrections underneath that vacuum piece. Perturbative, I mean in frequency. And then there are non-perturbative corrections which are of the kind e to the beta omega. Now, I will make some simplification. I'll just write this e to the minus omega. Just remember that omega is then defined in units of beta.
so sorry, but I was spacing also.
Yeah.
OP is like, but one guy is on one end, the other guy is at the other end. What are the OPs?
So this is still a spectral function.
Uh-huh.
So start with the Euclidean correlator. Okay, so start with
Okay.
OP expand this.
Fine. Both these are the same. There's no beta, I beta by 2 separation.
There's no I beta over 2 separation so far. So this is a, so OP expand this.
Yes.
Use the fact that the OP then compute the OP tells you, then you compute the thermal 1-point function in the of the operators on the right hand side of the OP.
Yes.
The only operators that can't have 1-point functions are spin J primaries. No descendants get contribution.
Yes.
Okay. So this answer on the right hand side is completely dominated by spin J primaries
Yes.
plus which includes stress tensor contributions.
Spin J primaries and then only the 0 component.
Exactly. Only the time component.
Yeah.
Take that answer, analytically continue it to get the commutator.
I see. So you're taking the OP and then doing an analytic continuation, and is that reliable?
It's reliable because it's reliable inside the strip. So because the strip, see, okay, the problem is the OP would never have been useful in thermal field theory because of the periodicity problem.
Since you can enclose it by a circle,
Exactly.
that does not go across.
Go across.
Yeah, got it.
So I take 2 points which are not separated by more than beta over 2.
Right.
OP is convergent. In that remit, I can expand this, write everything in terms of thermal 1-point functions, and then analytically continue get a formula for the retarded correlator, and then from the retarded correlator I can get one for spectral function. Okay, and what has happened here is I have done all that exercise. In fact, Eliasu, Mahajan, Perlmutter, Simon Zaffin, and one more person did this 8 or 9 years ago, what they call the thermal OPE. And you can take that data, and people also Fourier transform it, you can Fourier transform it back and recover what the answer is in Fourier domain. That's all been done here.
Sorry, I know this already, but for just a non-rotating black hole, isn't it just...
For now, no black holes.
But then why...
This is just a statement about correlation functions.
But okay, in general, you have all the higher point from the stress tensor also activated.
Spin J primaries include stress tensors.
No, I'm saying, but no, for a black hole, it would be some very simple set, right?
Yes, I'm coming there.
He's just saying from symmetry.
From symmetry,
Yeah.
I agree.
Okay.
So you're accounting for all the operators that
Would contribute.
OP,
Yes.
but I mean, you don't quite know. I mean, they do depend on the.
So I'm going to tell you something about the OP momentum space in a second.
The analytically can be term by term or only after summing it?
Term by term.
That is okay.
That's okay. Basically, each term in position space will give you some kind of, some Gegenbaur polynomial. You do some usual partial wave expansion, and then each partial wave you do.
And it's okay because it's convergent.
It's convergent
Good.
in that.
Yeah, but we are analytically continuing outside, right?
For now, no. This is still in position
In
space.
the strip, I know.
In the strip. I'm still in the strip. I'm then going to infer something about this. Okay. And I'll tell you what property is of this spectral function is reliable from the OP. So this is a structure I expect. In fact, I'll tell you that this part is not reliable from the OP. This part is, and I'll tell you what contributes.
Just to understand the structure, the first term is like the identity term.
The first term is like the identity term. So the perturbative part will start with a 1, and this is just a statement that I find in Fourier it's very easy to think about this if you look at high frequencies.
Right.
Then you don't see the thermal state. You should just see the vacuum answer. This is the vacuum answer. Okay. So this perturbative piece includes something that people like to call the thermal block. Okay. So it apart from these 1-point functions that we just discussed, the 1-point functions of various higher spin operators, it has some dressing in terms of frequency, and it comes from these Gegenbaur polynomials, the partial wave decomposition. And that spectral function block in momentum space turns to have some interesting features. Okay. So the kind of features it has is that it has the perturbative piece, which is controlled by this thermal block, vanishes when some nice things happen to the operator you insert. I don't expect you to pass all of this, but let me tell you what this means. This first type of zeros is the contribution from multi-twist operators.
Sorry, just for orientation. This perturbative piece is just the power law that you would have got in vacuum, 2-point function power law.
This perturbative piece is from vacuum,
Yes.
but that's the identity exchange.
Yes.
But then there are also
There's images. No, sir.
the corrections from other higher spin operators.
Yes, those are the what you call not.
But that's also in the perturbative.
That's also in perturbative. So then I missed.
The OP doesn't know about the non-perturbative.
Oh, I see. I see.
That's going to be the problem.
I see.
Yeah.
Yes.
Yes. So the perturbative pieces are also power law,
I see.
right? Because they're like saying, I exchange higher spin field.
Yeah.
So that will correct the vacuum piece to some power law.
And if you just took this perturbative, you did it operator by operator, will
Yeah.
you see the periodicity?
Give me 5 minutes and I'll tell you an answer to that question. Let me simplify the problem and then tell you the answer to that question. Okay. So these perturbative corrections, so this part is coming from things like operator derivatives, operator. So that's what I just call the double twist operators. And the second guy is some accidental vanishing, which has in particular consequences because it says that some multi-stress tensor contributions vanishes. Okay. This is not true in position space. This is important. In position space, it's not true that the double twist contribution vanishes. It just so happens that when you do the Fourier transform term by term, the double twist contribution for these special dimensions vanishes. Notice that all these dimensions have to be integers. Because
it's a consequence of some sort of a double discontinuity. Like that.
I think something like this. I will give you an answer also in a bit, which is sort of a bit more intuitive from the bulk side.
Your delta and delta zero?
Yeah. So delta zero is the operator dimension of the operator whose 2-point function of compute, and delta is the dimension of the delta and j are the dimension of the operator I'm exchanging in the OP. Okay. Now, so this set of statements is generic. I didn't use anything. I just used OP. But now imagine the following. Let's look at some CFT that's is also holographic. Okay. Now I'll invoke large N, and the fact that the OPE has only roughly 3 pieces. It has what Shiraz says is identity. It has these double twist guys, and then it has stress tensor exchange. Stress tensor and multi-stress tensor. This double twist also includes various spins.
But that would be like the O stuff, right?
Yes.
About the T stuff.
The T stuff will also have T square, T cube,
Yeah.
blah blah blah.
Because
Yes.
their dimensions will be graded in T,
Exactly.
while this will have offset of 2 delta O.
Exactly. However, since I want to look at the case where some of these things vanish, my operator dimension is integer, double twists are integers, stress tensor exchanges are integers, so there is a potential for something nice to happen. Okay? Yes. So indeed, so this includes multi-stress tensors. So these have dimensions n times t.
The large n counting allows for multi-stress tensors.
Exactly, it does.
Because the 1-point function of a multi-stress
Multi-stress is still
has the extra powers of
extra,
extra,
exactly.
which will compensate.
Yes,
the
yes,
extra one over
yes.
extra. So, yeah.
Yeah. Now,
And this delta O you said is an integer?
so when delta O is an integer, then we'll see. I'll tell you a consequence. What happened because of this holographic OP. Okay. When it's an integer, let's say in n equals 4 for somebody in 20 prime. Okay. Then no double twist exchange and maybe just a handful of stress tensor exchanges, or maybe not even that. But one stress tensor exchange because 1-point function needs one graviton exchange needs to exist. Okay. So basically this OPE part collapses completely for such operators.
That's incredible. Which means that you can just compute it, right?
No,
Okay.
because you need to control the non-perturbative part
Non-perturbative in what?
in frequency. Because you see, we are doing power laws, right? We are doing OPEs. So they came with time power laws. Fourier transform, they'll only give you power laws in frequency space.
But if it is the fact that it's convergent means that you just submit and then you get.
I'll give you an answer. You'll see, it's not the answer. Okay. Okay.
Can I just ask you, in the n equals 4 example,
Yeah.
at finite temperature, let's say you take the black hole,
Yeah.
what do you exactly do to compute this? You take the 2-point correlation.
I will give you the answer. Hang on to it. I will give you an exact answer for the 2-point function.
So for the vanishing, this double twist, you don't quite need this integrality, right? It's for the multi-stress tensor.
No, I don't think need the integrality for the double twist.
No, that delta minus 2 delta will be an integer.
Oh, sorry, at large n, yes, you're right. You're right.
Only for
Yes.
the other guy.
Yes. Okay. Let me, since this question has come up many times.
I'm really sorry. So what is the statement that if you had a holographic dual,
Yeah.
then you take you take the same operators,
Uh-huh.
and you get the decomposition is the identity and something which is a double trace or O, let's say,
Yeah,
and then stuff which is due to
stress tensor.
Okay, it seems right.
Okay.
What you expected additional IS?
No, not in the holographic theory. Because you
Large
know,
and-
the
of
only,
large and
only
small.
object that has 1-point function
Yes.
in the background
Yes.
is T.
T.
That's what I was saying.
Yeah.
Yeah. In a general theory, let's say you turned on alpha prime corrections, then you will get everything.
Okay. This is not going to be my focus of my talk, but just to orient you, I'm going to give you a formula, which is explicit. So this is something you can just do. You don't need holography for it. But the spectral function in any 2D CFT on a plane times say R11 frequency beta is some simple product, Bose-Einstein factor, product of gamma functions. Okay. You can compute it from BTZ, but you don't have to. You can just take your favorite formula 1 over ZZ bar to the delta, conformally map it to a cylinder, analytic continue to Minkowski signature, compute the discontinuity across the light cone, Fourier transform. Okay, so you will get this answer. Okay. Now, so let me go back to the other question.
Sorry,
Yes,
again,
yes, yes.
very elementary question.
Yes.
Embarrassing. If I wanted to compute OO,
Yeah.
this double
Multi-
trace operator,
yes.
holographically, what computer, how would I do that?
How would you do that? Yeah, yeah. So okay, so you can do the following exercise. So this was done also, and I was going to postpone this, but let me tell you the answer right away. So imagine for a second that you didn't know this momentum space decomposition, and it's only in momentum space that the OO doesn't contribute for special dimensions. Forget about the OO contribution and pretend that you only get contribution from multi-stress tensors. Okay. Now, multi-stress tensors are like contributions from gravitons. And then holography. So if I want to read off graviton contributions,
It's just product of what?
what
Individual 1.1.
yes, but you can do you can do something better. You can go solve the bulk wave equations.
Yeah, that's what I was thinking. Then you include the back reaction.
Keep back reacting the way we know how to do it. Just compute the higher point functions, moments of t to the n. But this is effectively doing some Pfefferman-Graham like expansion.
Moments of t to the n because of the black hole.
Because of black hole. Because of black hole.
Yeah, sure.
But also because of your operator.
But I'm thinking that finally you're taking 1 point function of stress tensor in the black hole background without the operator. Because you're using OPE.
Yeah, I'm using OPE, but I could sort of start with looking at how they contribute to the
You're now
OPE.
thinking of it as a 3-point function.
I'm thinking of it as a 3-point
In the
function.
bulk, you'll have to do the.
I have to do the 3-point function.
In the presence of the
Yes,
black hole,
yes,
right?
yes.
And then compute.
And then I have to compute it.
Now I get it. Because you also want the coefficient.
I also want the coefficient.
That 3-point function. I
Yes.
get it.
Okay. But this you can do asymptotically.
What was the question?
Okay.
What was which question? Sorry. My main question was how would you compute the OO 1 point function holographic?
Yeah.
It's one of these Legendre transform.
Yes,
right?
yes. But that will only give you the 2-point function of OO, knowing the 2-point function of O, or 1-point function of O. The Legendre transform thing is only a change of boundary conditions.
Yes.
It doesn't give me the OPE coefficients here.
Nice. Yeah, the 3-point. Yeah, I get it.
So I need to do something more.
Yeah.
It depends on the contact terms and so on, right?
Exactly. But in particular, if I know what the actual OPE decomposition is, I can start working this out.
I'm really sorry, and this is probably I told this, but to compute the double trace part, what would you do? You turn on the two O's on the boundary, you compute the back, and then what do you do? Sorry, this part is not.
There is no simple calculation. I actually have to know the OPE.
I mean, in the bulk,
But you would need to know the contact term, right? You would
Yeah.
need to know the 5 to the 4 term.
Yeah.
in the bulk.
In
Yeah.
the bulk,
So
you may have
suppose
derivatives and such.
Yeah, yeah.
But suppose I gave that to you, then you
But that's not what I want to do.
just since you were describing the calculation.
No, I was describing something else. I was describing that this calculation, even for the stress tensor, requires computing 3-point function.
Yeah.
So
Something simple for just for that.
no, because OO is not a simple operator.
Yeah, that's what.
OO doesn't have a field in the bulk.
Yeah.
So
This is the general.
there is no mapping between double twists and bulk fields.
So just to separate the issues, there are 2 questions. First, if I just wanted to compute it, 1-point function of OO, 1-point function of some number of stress tensors, that is presumably some easily done
Yes.
kinematically.
Exactly.
But you want to do more because you want to produce, you get this O with O,
Yeah.
you get a coefficient times this.
Exactly.
You want to also compute that coefficient.
Exactly.
That now
Now that
various-
depends on various things.
OP coefficient, right?
Yeah,
OP.
yeah, yeah, yeah. I
That
need the
depends on various
yes,
kind of
yes,
dynamical things.
yes, 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 yes.
So just separating those two issues.
Yeah. So
You were talking the 1 point.
I was talking just
Yeah.
Oh, I see.
that is a
that
stress tensor will just compute 1-point function of T and multiply.
and multiply because it's factorized. It can guarantees that you just factorize exactly. Good. So let me say in words. This might get confusing, but let me say something in words. You could try to compute the contribution of the multi-stress tensors by looking at the contribution in the presence of sources for OO, 2 sources on the boundary, by working out perturbatively in Pfefferman-Graham expansion, what those sources do. So this was done by Fitzpatrick and Huang 6-7 years ago, and more recently adopted in the context of what I'm going to tell you by Cheplak, Liu, Parnachev, and Wallach. And here's their statement. Ignore in position space the double twist contribution. Just compute and resum the contribution from multi-stresses by doing this Pfefferman-Graham like asymptotic expansion. Okay? Should you do that and try to compute the spectral function or this two-sided correlator or the Rita-Green's function, whichever one you want, you will find that that object is not analytic inside the fundamental strip. It tells you that you're missing information and you can use it to constrain what the double twist contribution is. And when you get that, when that dust settles, you can show that it pushes the singularity outside the fundamental strip to the domain where it's allowed to be.
That requirement of analyticity is enough to fix even
Yes.
what you need to fix the code.
And actually, for the double twist guy, there's no missing OP data. Right?
There is no missing OP
Because
data.
that is just a classical.
Classical, exactly.
For that, yes.
Yeah, yeah.
So this missing OP, I mean, I understand, for example, the coefficient of T, which will depend on the temperature and everything.
Temperature and the bulk coupling.
Yeah, the exact theory of gravity. Similarly, of course, O will also depend on the bulk.
No, I was thinking a leading order enlarging.
Yeah.
O.
It's fixed by the O.
Expansion is just the Taylor expansion.
Yeah. You just fixed by the OP coefficient of O itself, right?
So there you don't need, there's no data missing.
But the finite temperature.
I feel that just the OP, this doesn't even see the temperature.
Because it's a local statement, it's an OPE statement. It is always a local expansion for coincident points.
So somehow the finite temperature data comes in the expectation value
Exactly.
of
the operator.
Yeah.
Yes. Okay.
So in this case, you were able to compute this explicitly, and in general, one cannot, because why is the what is two dimension by?
This was just an example. I'm going to write down the formula.
No, but this is a general theory, right? Or
This is general, yeah. This is completely general in 2D CFTs.
yeah, because this 2-point function is just fixed by conformal.
Correct.
Can we not do this in general? Do this method of images and compute?
No,
In higher dimension?
no. I'll tell you why.
Because the black hole is not.
Yeah,
Yeah.
but what goes wrong with it? Because the microscopic, the behavior, microscopically it should be power law.
No, the microscopically it's power law, but here I had to use something about global conformal symmetry. The fact that I can wrap the plane into a cylinder.
Here you use that it was method of images on the other side.
Yeah.
So because BTZ is like thermal
Yeah.
ADS on the other
Other
side.
side, yeah.
So the method of images just really works
Yes,
on
yes,
the appropriate
yes.
side. There's no statement
Yes.
like that.
You could do what you're saying for the thermal areas, but you would get the thermal areas answer after image sum, but not the black hole answer. I'll tell you another technical statement which will make this obvious from something else. Okay. How long am I going to go?
Lunch is 1:15, 1:20.
When is dinner?
Now you're getting Russian style. Rajesh once told me,
I know the story.
the secretary came and asked, fish. Then they broke for lunch.
Okay. Now, I'm going to answer Abhijit's question about higher dimensions, and I'll give you a formula which looks suspiciously like this, but with some hidden complicated pieces. Okay. I'll motivate the formula. Maybe I'll first write down the formula and then I'll motivate it. Some number which depends on the conformal dimension. Times some very similar looking gamma function. Something else. all that has happened is that this momentum, which was the spatial momentum in 2 dimensions, gets replaced by some parameter, which I will explain what that parameter is. And there's a multiplicative factor, which I will also explain what that is.
This is general hierarchy.
This is general hierarchy.
But for some special value of delta? No.
No,
So any CFT.
holographic.
Holographic.
Okay, and sorry, I should have said this at the beginning. I'm only saying this about scalar operators. You know, operators O could have had spin. I think there's a similar statement, but it's not been worked out. So I'm pretty sure there's a statement of this kind for stress tensor 2-point function, conserved current 2-point functions, but for an arbitrary higher general operator, I don't know the statement. I believe there is. Okay, should be obscure, not obvious why this is true. Let me rewrite it before I do something with it. Okay, let me leave that aside for a second.
So this object has all the quasi-nominal poles, right?
It has everything. It has everything.
Just set the gamma to be a...
Exactly. So if you knew what sigma is some placeholder right now, it's completely obscure, then indeed as Shiraz says, you'll be able to find everything analytically.
The contribution from double twist operator will be suppressed in one line, right?
Yes, but not in higher triple twist and so on will be suppressed, but double twist is not suppressed in the 1/n expansion.
Double twist, do you mean double T or?
No, it's the,
That will not be suppressed.
it's
Not in general.
not in general, no.
It's just Taylor.
Yeah.
O with O, giving O has no manual.
Yeah. So if you, well,
But you are computing 4-point function and taking 2 operators close, but 4-point function is suppressed in that.
yes.
Not O.
Yeah.
It's like taking product of 2 points.
Yes.
That's how.
Yeah.
Okay. E to the W, you write, it's an entire function.
I'll tell you what it is. Okay, so some obscure formula right now. So let me unpack this. So e to the W here is a semi-classical Virasoro block. Let's say in bosonic Liouville CFT, in the limit b goes to 0, let's say, that's semi-classical, where the operators in question involved in the block have their dimension specified by geometry, omega, and q.
So you're getting higher.
Yeah. Okay. So I'm pulling out of a hat a 2D CFT, which has nothing to do with my higher D CFT, but it controls this 2-point function. Okay.
And that Virasoro, because it's supposed to somehow gather contributions from all multi-stress tensors.
This answer is the entire answer. Everybody. Yes. Okay. It's everything. Okay. It should be surprising. I'll explain where it comes from.
And this answer knows about the periodicity?
It's computed in the bulk from solving.
So it has to.
It has to know everything. Okay, so how did I get this answer? So what we are going to do is solve bulk wave equation. In this case, Klein-Gordon equation for some field phi, where phi is the field dual to O, so mass squared of phi is delta times delta minus K. delta over times L over minus T. It's a fact that you can verify, but I don't know why it's true or why it had to be true, that such bulk wave equations are what are called Fuchsian ODEs, by which I mean they are Sturm-Liouville type second order linear differential equations with only regular singular points. So at every singular point, Frobenius expansion works. Okay. And the singularities are at, okay, let's write down the black hole metric.
To know irregular singularity, that's the definition of Fuchsian.
That's the definition of Fuchsian. Okay, so I'll just do Schwarzschild, but the statement is actually quite general. It doesn't need to be Schwarzschild. I think it's true. I certainly know it's true for Reitzer-Nordstrom. I believe it's true for Kerr, but I haven't checked. Actually, it's true for Kerr.
The curve would not be an ordinary differential.
After using Carter's constant, the appropriate Tucholsky analog of ADS Kerr equation is of this form.
It separates from ADS.
It does. It not only separates for ADS, it separates for ADS in any dimension.
This is any.
Because there is still a killing Yano tensor for arbitrary Myers-Berry ADS cycles. It separates for any maximally symmetric spacetime. So, right. So where are the singularities of this differential equation? If delta is not integer, then clearly r equals infinity we know is a Frobenius singular point, because the fall offs are 1 over r to the delta and 1 over r to the d minus delta. So that's one. Turns out the black hole singularity is another. We also know the horizon, the outer horizon, is also a regular singular points, because the solutions go like r minus r plus to the plus minus I omega over 2. However, this function which enters the wave equation has d roots. So all of those are singular points, and I will just not try to draw them in general, but let me draw them for ADS 5. There are 4 of them. Now, if you go open the big yellow book, there is a statement. There's one place where Fuchsian differential equation shows up. They show up in many places, but one obvious place they show up. They show up as BPZ equations for null state decoupling in 2D CFTs. Okay. So famously, the 4-point function satisfies hypergeometric. The BPZ equation reduces the hypergeometric equation. This is the hypergeometric analog of this Fuchsian equation, the BTZ example. There's 3 regular singular points. The singularities are at the so-called black hole singularity, which is at r equals 0. At the outer horizon, there's only 1 in this case, and then at infinity. That problem is solvable because we know the connection formula, thanks to whoever, for hypergeometric functions. So this is something that we've all done various times in our life. We can just write down this answer without ever having known about 2D CFT and this conformal map. We could just solve the wave equation in BTZ and write this down. Okay. So in higher dimensions, the equation is Fuchsian. Right. So I can take that Fuchsian equation and I can interpret that Fuchsian equation as the equation governing some decoupling of some null state. Turns out the null state is at level 2, so that has to be the case because it's a second order differential equation. And that so far is slightly pointless because it's just saying same equation shows up in 2 different places. You still have to solve it. The interesting part was about 5 years ago, these folks in CISA, Bonelli, Tanzini, and their collaborators came up with a way of using Virasoro conformal blocks to derive a connection formula for such Fuchsian differential equations.
Connection formula means smaller expansion of large expansion.
Exactly. So in particular, let's ask what do we want to do. So let's elaborate on that point. So there are two follow-ups here. And two follow-ups here. So this is normalizable. This is not normalizable. Plus is outgoing, minus is ingoing. So what you want to do is you want to solve the wave equation with ingoing boundary conditions here and non-normalizable boundary conditions here. That will give you the two-point function. So if you find that connection coefficient, the sort of map between the local Frobenius basis here and the local Frobenius basis here, you're done. This follows from that map. They actually did it initially. Okay, so historically it wasn't done this way. They weren't the first people to notice this. The first people to notice something like this was Albagrassi with Hatsuda and Aminov, who noticed that, in fact, they didn't even notice it for ADS black holes. They initially noticed it for Schwarzschild black hole in flat space. There, the difference is infinity is different, because in flat space, you don't have these power law follow-ups. You have an exponential Coulomb tail. So the exponential Coulomb tail tells you that the singularity at infinite is an irregular singular point. It's not a regular singular point. The equation is not Fuchsian, they're Fuchsian with some irregular singularities. So not technically Fuchsian in my book. But they realized that the differential equation that shows up there is the same equation that shows up in the solution of Seiberg-Witten theory if you're trying to compute the Nekrasov-Shatashvili partition function. So you can write down a formal incident on expansion for that answer, and from that they recovered the quasi-normal modes of Schwarzschild and Kerr. They could solve it that way. Okay. Then these folks, Bonelli and friends, realized that that problem could be readapted and rewritten this way. Now I could shortcut the answer to the conformal block by telling you an acronym AGT. It's sufficient to tell you that n equals 2 Seiberg-Witten maps to 2D CFTs. Okay. But I will not use the instanton story at all. I will just tell you the answer in 2D CFT language. Yes. I agree.
Is it that you have these modes hugging the horizon which are left and right moving in some sense?
I don't think so. I think it's much more obscure than that, and I don't think there's any underlying 2D CFT reason for this answer. I'm willing to bet that the black hole problem does not have Virasoro symmetry.
If I were in Euclidean signature,
Yeah.
I would have thought that R equals R plus is like
It will collapse, yes.
it caps out.
Yes.
So is there some like geometric way of visualizing this plane where, I mean, I'm just confused that if you do it in the Ren signature, there's this disk which is opening up inside R plus.
Yes.
But in Euclid, yeah, I mean, sorry, I don't have.
No, but remember the connection problems are very different.
Okay.
Because here the connection problem you say pick the ingoing mode
Okay.
and then match it to the
Okay.
in a normalizable or non-normalizable mode. In the Euclidean problem, you just say pick the smooth modes, which are confined to sitting at Matsubara frequencies, and then determine what happens at infinity. And at infinity, the only there's of course no distinction between normalizable and non-normalizable. The only thing you're allowed to turn on is non-normalizable in Euclidean signature. So there's a unique solution, there's a unique Green's function, it's a different problem altogether.
So at leading order, the two-point function is supposed to come from this OP, right, with those operators in OP.
So I'm going to simplify that formula in a second. But for now, I'm telling you that this is much beyond the OP. This is some exact formula that we pulled out of a hat from using this technique.
Yeah, you're not using the OP at all. You're
No.
just computing the kernel to byte.
No, exactly.
But if I want to now interpret it,
Yes,
then at least the perturbative part would agree with this stuff.
it has to. It has to. It has to. I'm coming to it. Hang on to that question. It's important.
So I was just trying to see what, the thing that Sandeep said was the Virasoro thing. So is it, so the Virasoro, at least in 2 dimensions, the way I would think of it is that it somehow resums the contribution of all the multi-stress tensor
Correct.
blocks.
Correct.
Right, global blocks.
Correct.
So is it that there is some sort of a symmetry governing multi-stress tensors?
Hold on to that thought. Just hold on to that thought. Yes. So in particular, let me say one statement before I give you my punchline. In 2D, this entire contribution only comes from multi-stress tensors. There is no double twist. Yeah. So you're completely right to say that this answer, because it's full, knows about double twist and the stress tensor. And what you're asking is a statement I'm going to write a statement for in a second, which is to say, for some cases, I can separate them. Okay? Sandeep.
No, you must go just so this whole development, some major advance in mathematical physics and perception, is some generalization of matched asymptotic expansions we do perhaps, but now for without small parameters of potential.
Okay, caveat, okay? Statement is very powerful. I need to tell you what sigma is, which I haven't still done yet, and you need to be able to control the block. So anybody who's played with the Virasoro blocks knows that they're controllable, but only in OP expansion. So you need one small parameter, because they're determined by recursion. So you need some small parameter depending on your channel. So it could be S channel block or T channel block.
It's not just the identity block, sorry.
It's not the identity block, it's a full block. It's a 4-point block for 4 external operators whose dimensions are specified by parameters. So it's not that.
You say you can compute these connection coefficients, but not compute the whole solution. Is that right?
That is correct. Yes, important point. Thanks, Shiraz. So the wave function is not accessible. The connection coefficient is accessible. Yes. In fact, this is important for the following reason. Should the wave function have been accessible, then just to say something tangential, the program we developed with Loga of trying to compute Schwinger-Keldysh correlators relied on 2 pieces of data: the bulk to boundary propagator and the bulk to bulk propagator. If the wave function was accessible, we would have explicit formulae for both of these things, which means that you can't just do 2-point functions, you can do arbitrary endpoint thermal correlation.
This Virasoro block, what is the dimension of the internal operator?
I'm going to write down.
This Virasoro block is for some particular 4-point function, or
Well, the way I wrote it, it's for arbitrary d-point function because it's in d dimensions, but in 4 dimensions it's a 4-point function.
of the operator you initially are considering, or some relation with
No, it's not. As I said, this does not have anything to do with the operator I'm considering. It's an auxiliary 2D CFT determined by the wave equation.
I see. But there's some operator in the auxiliary to these.
I'm going to write it down.
Sorry.
So this is the boundary. This is the horizon. This is, let's say, the complex horizon. And this is the singularity. And to make my life simple, in 4D, you have 1, 2, 3, 4, 5, 6 singular points. Okay. But apply a projection map from the complex R plane to a complex Z plane where Z is defined to be. So R space is double cover of Z space, and so two of the singularities coalesce. So these two merge, these two merge. So when I say complex horizon, I mean the horizon at IR plus. Okay, so this is at IR plus, this is at R plus, and then the other 2 points are 0 and infinity. Okay. In this auxiliary 2D CFT, you insert an operator whose dimension is set by nu, because the fall offs at infinity are r to the delta and r to the d minus delta. So a semi-classical Liouville block involves Liouville momentum proportional to nu in this formula. Here at the horizon they are plus minus omega, so this is set by omega.
And complex.
Likewise at the complex as well, it's also set by omega.
I mean, two of the dimensions are
Complex, yes. So it's plus minus I omega. They're purely real here, but they're complex conjugates here. And the last thing is funny. A singularity is an operator of dimension 0. It's not the identity in Liouville, but it exists, whatever it is. Okay. It's just the nature of the equation. Okay. Now, the last thing you need to know, it's the 4-point block. So when you fuse these two operators, the momentum, Liouville momentum running in between is sigma. So that's what sigma is. So, okay, I should say something about differential equations, which is helpful. The hypergeometric problem is solvable because there are 3 singular points. And Fuchsian equation with 3 singular points are completely determined by the local singularity structure, by local exponents, Frobenius exponents. Higher dimensional, higher order Fuchsian equations are determined by the singularity, the Frobenius exponents of the singularities, and one piece of data. One extra piece of data is what's called in differential equation language accessory parameters. Okay. So notice that nothing in this problem with these dimensions knows about the momentum. The wave equation, of course, knows about the momentum. The accessory parameters know about the momentum, and then they feed into determination of sigma. So the problem is complicated because I have to compute this particular 4-point function in 2D CFT in the large central charge limit. And these are rescaled operators. Okay, for the expert, these are dimensions after rescaling, semi-classical dimensions.
Nu sets the whatever linear digital slope of the
it sets think of it as the momentum of the Liouville field at infinity. So think of operators e to the b, how do you like it, alpha times q minus alpha, something like this, phi. So alpha is like b times, so q is b plus 1 over b. Alpha is like b times b at infinity. Something.
Which is slope of linear digital.
More or less. It's a linear order, but b is going to 0. So that. Yeah. Good.
And this technology is well enough now.
This technology is easy. This is something that you can compute.
No, it's not work.
Yeah.
I mean, so 3-point functions in Liouville theory, there are selection. You've got one momentum, another momentum.
It can go to any momentum, right? Any momentum.
Does not even discrete, does it?
No. So if you want Liouville theory, let's do Liouville theory on Wednesday.
Okay.
Barnes gamma functions, Barnes double gamma functions. Yes, but
I would think very vaguely that Liouville theory has an e to the power
yeah,
phi.
yeah,
That is what breaks the translations and everything.
correct.
So I was thinking very vaguely that momentum will be conserved up to shifts in that.
Yes.
Is that correct?
No, that's true. But well, let me say the DOZZ formula just says that the 3-point function exists between any three figures. What you are thinking of is selection rules that are visible in Coulomb gas in the perturbative limit. Better than, yeah. So, okay, good. The one other piece of data I haven't told you. This is a 4-point function, but I haven't told you where these operators are in the 2D CFT. Okay. So maybe you can map them this to 0, maybe this to 1, this to infinity, what you have. But there's a fourth point where what is the cross ratio? And as luck would have it, the cross ratio in this black hole problem is fixed. It's fixed by geometry. It doesn't care about anything else. It's half. Okay. So this makes the problem hard because you can't do small x expansion or small 1 minus x expansion. Okay. Now,
Is this the point of bootstrap people like? Expanded on this point?
no, but this is, if you want to expand around this point, the block needs to be resummed to all orders, the non-perturbative statements in the blocks. If you want, so the people like, so if you want to do usual computation, the place that's nice to expand is around x equals 0.
No, what I mean is the numerical bootstrap people.
It's a crossing
It's
symmetric
a crossing symmetric, it's a S to T crossing symmetric point. So if you want to match S and T channels, this is the place you would like to match.
Is that x going to 1 minus x?
Yes. Okay. I'll make a auxiliary comment. It's not related to the talk. This x depends on geometry. In fact, it purely only depends on geometry. It doesn't depend on the operator. Okay. After you choose the right variables to do this mapping, things become nice if your black hole has a hierarchy of scales. Hierarchy of scales. So I'm talking about planar black holes in areas. So there's no hierarchy of scales. There's only one scale which is set by R plus. But you could do global black holes in areas where there is a hierarchy where there are small black holes and large black holes. In which case x depends on the black hole size in areas units. So for small black holes, one of the channels becomes better and better. One of the channels becomes better and better. Either x or 1 minus x becomes size.
Becomes smaller.
Or near 1, not 0, 0. Same thing for charged black holes close to extremality. Extremality gives you an x that's controllable. Okay. But those are the examples I know where this is plausible. But in general, you're sort of out of luck. So this formula, while useful, it still requires a lot of work to get W and sigma, which is determined from W. Okay. So I won't write the formula for sigma, but it exists in the literature. The formula
Dependence of sigma on momentum,
that's determined through, once you know W, sigma is determined through W. So that fixes momentum dependence into sigma.
So where is the momentum in W?
W, because it depends on the accessory parameters.
But that's the sigma, right?
So you go back and solve the wave equation,
Okay.
and then you can get the determinant depend on sigma. Let me say one more thing about sigma before telling you something else. Now, in its problems, you have a basis of solutions here, you have a basis of solutions here. So the basis of solutions, the local Frobenius basis here, and the local Frobenius basis here, are related by an SL2 matrix. A 2 by 2 matrix, which sort of tells you how to match solutions from one side to match solutions to the other side. Okay. Something that's nice about this 2 by 2 matrix is the monodromy, which is the monodromy of any contour that encircles these two singular points. Right? Because the fact that these are singular points of a differential equation means that the solutions have branch cuts at these points, and the solutions pick up monodromy as you go around them. But you can take joint monodromy around some cycle, and there's a nicer way of saying what sigma is, purely geometrically. Let me write this down up here. So it's an invariant of the differential equation. It's a trace of the monodromy matrix along which, because the trace doesn't depend on the contour between horizon and infinity.
And you know this monodromy matrix?
Coming. No, as of now, no. But first of all, I'll tell you why. And okay, it's up to a factor of 2, but it doesn't matter. But so far, just another obscure statement. Now I will simplify. Okay. Okay. So just to recap, I argued for some structure from the OPE and told you that from the OPE I could tell you something about contribution from double twists and from stress tensor, but there was no simple decoupling of them, except for some special dimensions when they seem to decouple, where the double twist contributions in momentum space vanish. Momentum space is nice vis-a-vis holography because I can solve the wave equations simply by solving ordinary differential equations. And there's a formula for the spectral function which knows about everything. So we can go back to the question that everybody's been asking, where is that information in this formula?
Sorry. Is sigma exchanged or only sigma or sigma and minus sigma? The cost seems to suggest both.
Both. Because you see, it's a level 2 what do you call it? Null state that decouples. So
So this monodromy is just the usual monodromy that if you exchange something, you get a monodromy.
Exactly.
Because you get sigma and minus sigma.
You get that, exactly. So it's the same monodromy both from the 2D CFT point of view and from the...
Sorry.
Yeah.
Where is the Q dependence in this formula?
Sorry?
Where is the Q dependence
In the formula, it's buried in both what I erase in W and in sigma.
Is it in this figure?
So think of this as function of omega and Q. Because given the wave equation, what is exchanged cares about Q. But I don't have a simple formula for it, except in some special limits. That's the problem.
Yes. And one more thing, can I see how can I get this for d equal to 2 from here?
From here? Yeah, so if I will write another formula and you'll see immediately how we'll get something. But in some sense, for d equals 2, I can say this immediately, sigma is just Q.
And that factor?
This factor goes away. So it simplifies or goes away and then nothing survives, it's just the gamma function. So,
This monodromy is this swap, right? I mean this R plus and boundary.
yeah, going around each other, yeah. But, okay, there's another fact about differential equations, that this monodromy that I drew is also this monodromy.
Also true in CFT.
Also true in CFT.
These two are
Open contours go the other way, yeah, exactly.
But this will tell you modulo 1.
Modulo 1, yes.
And is it meaningful only modulo 1 or not?
Not sure. Not sure. But it's an SL2 monodromy, so not sure.
No, but do the connection formula depend? I mean, does your answer depend on sigma modulo 1?
No.
It depends on sigma.
So it depends on sigma. In fact, I will cheat. Okay, I will cheat and never determine sigma. I will determine the monodromy. Monodromy is what we have control over.
But then if your answer would depend on sigma, then there's
Then there's an ambiguity. So, but you will see why I care only about the monodromy. Good. So I want to write one more formula, which is now completely holographic. And suggest doing one more thing. Let me say this is holographic function of omega q. If I take integer operators with integer dimensions, I claim from that formula, still obscure because we have not simplified anything, I can factorize the spectral function completely. One piece only knows about the OP, one piece only knows about the non-perturbative. This is exact, so we have evidence, it's not a mathematical theorem, we didn't prove it. I'll tell you what evidence we have. We have an argument for why this is only for these dimensions. Okay. The easy, fast, simple check, we numerically verified it by using the blocks. By using the homological recursion to compute blocks.
So this OP and non-perturbative part I still haven't you will explain.
I will explain this. That's the key point. So the whole talk has been going toward isolating this non-perturbative piece, and the piece that's under control, because we can do the OP anyway, is this part. And I'm saying that for these dimensions it factorizes. Okay. So the easy check is just take our formulae, which so far I didn't write anything for you on the board, but they exist, and then compute the answer here, compute sigma numerically, check this piece, and then check that it matches what you expect from the OP. So this we did. We also have an argument, which I won't go into now, which uses the fact that when this dimension is special, when u is integer, the fall-offs at infinity are integer separated. Okay. When fall-offs in Frobenius are integer separated, you either have logs, or when stars align, nothing. Okay. So when you have nothing, it just means that the differential equation looks like you have a singular point, but there is no monodromy around it because the wave function around that point is analytic. It does not have a cut. So these are called apparent singular points in differential equation parlance. There is a fun fact that when you have apparent singular points, they correspond to inserting in the 2D CFT language higher level null states. The rank of the apparent singularity matches with the level of the thing. So these statements, and this formula was Frederick and I proved by rewriting some of the statements from these folks in a paper from 2 years ago, and in particular where we explained why these apparent singular points are.
Just to be clear, when you talk about OP, the expansion that we are talking about is for large omega expansion.
No, this statement is exact. I'll tell you what non-perturbative is.
No, but exactly what is the OP expansion?
So remember that what happened when we had these special dimensions, the double twist had no spectral function contribution. So this has identity piece and has contributions from a finite number of multi-stress tensors, because we also had a second set of zeros coming from multi-stress tensor exchange. So this it's a polynomial of, so in fact I can tell you what it is right away. This is a polynomial of finite order in omega. The one term, so it starts out as omega squared minus q squared to the what was it, d minus 2 delta, or delta minus 2d? Okay, just new in this case. So this piece is the vacuum piece, and then there is t squared, but it stops somewhere. But because these are all governed by dimensional analysis, they only have some finite part of omega.
So non-perturbative also carries this t dependent?
Yes. Everything carries t dependent, because there are, think of my omegas and q's as being non-dimensionalized by factors of temperature, because they're beta omegas and beta q's. So I'm not going to write temperatures anywhere explicitly.
Is the non-perturbative term reflecting the fact that momentum space correlators don't actually obey an OP?
Yes.
So the failure of the OP.
Yeah. So
Momentum space, things all over the place.
Okay. And now,
And the non-perturbative rule?
Sorry?
You want to find the non-perturbative part of the row?
I don't have to find it because I'm going to write it.
This is what is the idea for any holograph, right?
Yes.
Integer, right?
Yes, yes. Okay.
So quite an explicit.
It's an explicit formula. It completely decouples the multi-stress tensor contribution from the non-perturbative part. This formula is explicit modular knowledge of sigma. Okay.
And just to check again, the non-perturbative part itself cannot be thought of as exchange of something. It's just representing the failure of the OP thinking.
Yes, yes, but it is the exchange of something, because somehow in the perturbative OP, see, the position space statement, the exchange was both double twist and stress tensors.
Yeah.
For these dimensions, the momentum space formula from the OPE does not get contribution from double twists.
Good.
So where did the double twist go?
If it does not get contributed, sorry.
I'm saying you take
in position space we had it.
we had it. The Fourier transform killed them because they are of some stupid gamma function zeros from Fourier transform.
Yeah.
But they can't disappear. They must be here.
But they did disappear because in Fourier transform you got zero.
But in this part,
Yeah.
in the OPE part, but they can't disappear in the full.
So again, it sounds to me like failure of OP.
Yeah. Exactly. The momentum space OPE for these particular operators knows only about identity and a few order of multi-stress tensor exchanges. So it's not capturing the entire information.
Can I say it is still valid as an asymptotic series? I mean, if you say failure, because
Yes.
you still have this kind of decomposition OP, and then because I would have thought when it fails, and you cannot.
But there is an asymptotic series, and I'm just about to write an asymptotic series for you.
And asymptotic at large, omega.
Omega. Because you see, all of these are exponential pieces, right? The omega dependence is exponential.
Sometimes purely contact terms or something, like purely analytical in position vanish in momentum.
Yeah.
You know, so
But this is not quite that. Not quite
the
that.
double trace, I was wondering whether it's
I don't think so.
still a similar.
Yeah. Because it depends very much on operator dimensions being integers. It's not some generic statement about operators. All right?
And when the operating dimension was not integers, this structure may still be true, but you don't.
Yes. So if this structure is true for non-integer operators, I think we have exquisite control over the correlation. Because I'm going to tell you what this function looks like.
Sorry, I don't have complete knowledge of it, but what happens in twisted space?
I have no idea. I mean, it's not clear to me twisted space is useful for this discussion, right? Because this is a thermal thermal 2-point function in a conformal field theory. So,
Usually twisted space is most useful when you're on shell.
yeah, and this is completely off shell.
So what things would change if you had a global black hole, like a root structure or R that stays?
Everything stays, actually, yes. Not all that changes is X changes. Everything else is the same. You might want to do a different change of base coordinates to bring it down to this form. We have some evidence and a strong conjecture that this is still true for at least these integer dimension operators. But again, I think our evidence is weaker than the case that I'm discussing, so I don't want, but I'd be willing to put money on it. It's true.
Why there is no Q dependence in the non-perturbative?
There is in sigma. It's buried in sigma, so but it is there.
But we don't know explicitly what to do.
So far, no. I'm going to tell you something about it in a second. So this involved two pieces of data so far. One was, so I'm going to introduce one more technique. So first technique was OP, we've got some information out of the OP. Second technique was this Virasoro block mapping, got some answer from the Virasoro block. And now you're asking the right question, what am I supposed to do about this guy? Because this is good, but I don't know how to evaluate this function. The important part, and the part I want to highlight, is that if I want to control the spectral function, I don't need to control sigma. I need to control cosine 2 pi sigma. And like Shiraz said, it doesn't matter if sigma has ambiguities as long as cosine 2 pi sigma is well behaved. And cosine 2 pi sigma is a monodromy, trace of a monodromy. Okay. So I will control it, but I will control it in the manner Abhijit said, as an asymptotic series at large omega. Okay.
Not enough is about the reservoir block technology we just completed.
Oh, I mean, you can compute it to whatever order you want numerically. I can do it to thousands of orders, but it's not, there's no analytic formula. There's a simple recursion relation. I can write a code, codes exist, can be done, but yes. WCW? Sort of, but not fully. Yes. So in the Katzmund, but for compact Katzmund we do, but SL2 is more tricky than a compact Katzmund is. So if it was SU2, we would be in business. We would have written another formula.
So, but the sigma is just some local. Oh no, but it depends on the matching.
Exactly.
I see.
It depends on the matching. Yes. Okay. Okay, it's 12:45. I have two more things to say. So I'm going to skip one part, which is the part. So some of this is all. The new part is basically extracting cosine 2 pi sigma, and I'm just going to tell you the technique. The technique is something you know, but with an adjective. It's exact WKV. I'll just say it in words. So WKV we learn in school is best thought of as sort of like the Bohr-Sommerfeld formula. You just look at the turning points, you look at the period integral of the turning between the turning points, and you get the quantization formula. Okay. And you think of it as a statement at small h bar, large parameters, large energy, small h bar. But you can systematically compute perturbative corrections to WKV. You can take the systematically computed perturbative corrections and you can resum them. If they're asymptotic, but you can Borel resum them and then write down the appropriate asymptotic series after Borel resummation. What the answer is depends on where you are in parameter space, because the Borel transform doesn't always converge. The Borel transform is separated from convergence by Stokes domains. In different Stokes domains, things converge differently. So your favorite example of single turning point, the AD problem, local model for WKB has three domains where Borel converges. One is this upper quadrant. These are cube roots of unity. Along these rays, the AD function has Stokes, anti-Stokes lines. So you can sort of find the answer here, you can find the answer here, but if you're physically interested in real parameters, you have to figure out how to actually work out the answer on the real parameter line.
So the part where it's convergent, you can think of it like perturbative expansion and...
It's an explicit asymptotic series, it's a formal power series. It's not just perturbative in the parameter, let's say h bar, if you're thinking of quantum mechanics. It also has e to the minus 1 over h bar terms. So if you like, it's like, one instanton contribution e to the minus 1 over h bar with a prefactor that's perturbative in h bar, plus a 2 instanton contribution with a prefactor that's perturbative in h bar, plus a 3 instanton contribution, etc., etc. But It's in fact all orders of instant on expansion. Okay.
It's perturbative plus non-perturbative.
It's and that's why the qualifier exact, because it's supposed to get you everything. But once you've done this trick, so the technique is ancient. Technique is goes back to Voros in the 80s and has been very well developed. It has other connections, but the only point I will make here is that, again, I'm not trying to do Bohr-Sommerfeld quantization. I'm not trying to find energy levels. You can adapt the WKB technology to find expansion of monodrome. I'm going to tell you an expansion for cos 2 pi sigma. Actually, let me skip expansion for cos 2 pi sigma and just write down a formula for this guy. Okay, this means S jumps in steps of 2. Okay, there's one more sum, but this is pure phases. This is pure phases and perturbative pieces. But you can see here that this has various instanton contributions which depend on omega, and this d parameter is the last parameter I need to describe for you, and that will make the momentum dependence clear. There's some numbers, it doesn't matter, but let me write it this way.
So here you are expanding that expression, right?
Yes, the whole formula. Yeah.
But I mean, there was another formula that was here with the gamma function, leave the W and so on.
Yes.
And that is the rewriting of that formula?
Sort of, but for the following, in the following sense. So the e to the omega piece, e to the W piece, the Virasoro block, folds into this OPE piece. The cinch was there explicitly. The gamma product, because the gamma product has complex conjugates, I can use reflection formula a couple of times and bring it to this cos form. So this part is sort of not super elaborate from the gammas. The part that is interesting is the statement that the Virasoro block and everything else just folds into the OPE piece. It does not control the non-perturbative piece.
And then still, what this is giving you is multi-stress tensors then, right?
This guy? Yeah. Correct. So the Virasoro blocks still seems to know about multi-stress tensors, which is an amazing statement, which has no reason why it must be true. Okay?
It's not like a vacuum Virasoro block or anything like that. So
Yep.
there's no natural.
Exactly. It's not some universal statement that we can make once and for all. Exactly. Because it's not governed by the Virasoro algebra. It sort of is, but it also depends on the operator question.
And you said only a finite number of terms contribute. Virasoro block could
Have infinitely many terms.
Very
Yeah.
funny
Yeah.
stuff.
Yeah.
Yeah, so why does that happen then?
Huh?
Why does that happen then only from a block you only get finitely many terms?
Well,
except for the special values.
because what happens is truncation happens because x and because x is half and so on. There are many accidents that happen, and they seem to suggest that the Virasoro block itself in 2D CFTs has very interesting structures. X equals half.
I see. So x equal to half is
W does not have any sigma dependence. E raised to W, that W.
It does, because this OPE depends on also Q.
So this sigma actually is in the both.
It appears in both, yes.
I thought sigma.
Now sigma is like some derivative of W, but it's related to W. They're not independent objects.
And is it clear why these particular E operators
Others don't. Again, I think it's an accident of this particular Fourier transform and these external dimensions. I think the real question is, suppose is the thing that Shiraz asked, suppose you look at generic dimensions, is something like this true? And can we say something stronger in that case?
Generic dimensions that X equal to half.
That in this case is true, but X may not be half, as someone asked about global black holes. X may be something else.
All of these things still continue to be true.
Some of these things still continue to be true. I don't know if all of them, because we haven't checked all of them. But yeah. Okay, and finally, now I can exhibit the Q dependence. The Q dependence is some hypergeometric function.
Wait, this was to some order in omega?
No,
This was exact.
this is exact. Well, this is this parameter nu that shows up here. In the instant on, it's a saddle point answer.
But it's, as S goes up, then
Yeah. Goes down, goes down, up. Yeah.
And this bracket.
Sum over what?
Which one? This sum?
This sum over Q. That sum.
The sum. This has phases and power loss. So all I meant was that it doesn't have any exponentially small pieces in omega. So,
So the perturbative pieces also you just absorb in the exponent, right? Because as you expand this out, then it will have 1 over omega pieces which will just expand.
they're in here as well. I mean, so think of
They
this.
will also come from here, right? Because
They will come. Some of them will come from there. Those have been absorbed here, but some are here. Yeah. And this is true for Q over W between 0 and 1. Okay. This is. So, this is exact. As long as Q is, as long as it's in the time lag range. 0 is tricky. 1 is. This formula limits to the right answer. I'll say something about 0 afterwards. Ask me later. There's something funny that happens, and we don't know what happens for Q bigger than W. We are using some particular features of how the WKB works, turning point structure and so on, and the equations as you change the parameters, turning point structures can change because the effective potential depends on the parameters. So Q equals 0, Q equals 1, Q equals W, and they're all different phases of this turning point structure. Okay. Now, so we have some 20 minutes, so I think this is sufficient information about spectral functions to say something about singularities. Okay. Now, this is some function of omega. If you strip off the cinch, it's the two-sided correlator. Okay, so the fact that spectral function factorizes means the two-sided correlator factorizes, because the two-sided correlator is the non-perturbative is the spectral function divided by the Bose-Einstein factor in frequency space. So you can also think the two-sided correlator has an OPE piece which follows from this piece, and there's a piece that's just basically this, the denominator here. So let's take the denominator if you like. It's given an explicit asymptotic series in omega. We can compute these coefficients to whatever order we want, but so we can then take this term by term and Fourier transform it to position space. Okay, so I'll get some function of time, but now realize that these are at fixed momentum. Well, I didn't say one thing about the thing. It's obvious from the formula. The fact that I'm saying Q over omega less than 1 and I'm taking large frequency and limit means that Q is also being scaled to infinity. Taken to infinity. Yeah. Q is also large. Okay. There are other limits you can consider where you keep Q fixed and take omega to infinity, but that will give you a different problem. But I'm going to talk about this problem. I'll come back to the other limit in a second. So anyway, let's look at the singularities of Q of this function CQ. So it's a mixed correlator. It's mirrored in position space because it's at some fixed momentum, and it's now in time domain because of Fourier transform this series. In the complex plane, it has singularities
Should really go equal. Q equal to 0 is so simple that it begs the question.
I'll say something about Q equals 0. There are some ranges of these are RS and sorry, this is, I should not call this Q, I should call this something else given my notation. Let me call this U. These are some integers with some ranges. Okay. There are singularities of this function in the complex plane at these points. No, just take that answer, Fourier transform in time, to time domain. Term by term. Okay.
So when different terms will have different singularities.
Yes.
That's why you get this shifted answer.
And U is also integer.
U is also integer, yeah. So, I'm just not writing ranges, but we know what the ranges are. Okay. Now, indeed, at zero momentum, either strictly at zero momentum, or if you want, you can think of it as large frequency but finite momentum. This formula has been known for a while. This is not new. It simplifies quite a bit. In fact, it's known in arbitrary dimensions.
So the singularities are outside the strip.
They're outside the strip because of the I beta. There are plus minus both sides. I'm writing only the plus side, so if you like. Okay. This is some ancient formula. This formula. Okay. So I'm going to call this T star, and I'll explain where T star comes from.
So, sorry,
Yeah.
this formula that you have.
Yeah.
So you're saying its Fourier transform is not periodic.
These are singularities.
How did that happen then?
I mean, I think the way I understand it is what we said earlier, that if you just look at the stress tensor exchange, even if you don't truncate, they don't give you some function that's analytic within the strip. Somehow the conspiracy in the OPE is that something happens between the stress tensor and double twist exchange that manifests analyticity within the strip at the expense of making the answer outside the strip have singularities.
How is the periodicity lost?
Well, but these singularities are at some real part of time, right? But then the R periodicity says that then they get imaged in I beta over 2.
I should really wait, but just going back to your earlier work with Steve Shankar.
It's not my work. It's not my work.
In a sense, are you saying you have these similarities, but they are not on physical sheets?
I'm coming there. Hang on, and let me answer Shiva.
It was something over R, but not R equals 0. I mean, you didn't get a singularity in this one.
R is not, I didn't write the ranges of R. R equals 0 is not allowed. Yeah, exactly.
So it's almost periodic, but not quite.
Exactly.
And can you trace, sorry,
Yeah.
can you get at the level of differential equation solving?
Yeah.
The differential equation would have periodic solution. Somewhere you've lost it. Can you trace of what's there?
Not obviously, no. Because no, actually that's not clear because the differential equation is momentum space, the one I can solve.
The one you can solve. So someone Fourier transform.
Because you see, the differential equation, well, okay, maybe Shiraz, when you say the differential equation is periodic, I think that periodicity is manifest in the Euclidean correlator. Okay, so if you solve the Euclidean problem, it's absolutely periodic, right? It's because the only frequencies that are allowed are Matsushita frequencies. Now, there's a formula for the spectral function in terms of the Euclidean correlator, but then you have to analytically contain the Euclidean correlator. Okay, no guarantees that that analytic continuation also doesn't lead to singularities. So conspiracy here is this OPE, if you like, is completely governed by that Euclidean answer. It knows about the Euclidean answer because that's how it's built up.
Wasn't the result of the earlier exchange that you had these branch cuts, so therefore
Yeah.
There was one thing, just at the level of solving, if you could pin down where.
Yeah. No, I agree, but
Yeah.
That has nothing to do with the similarities of the equations.
no.
So this by omega range is coming from the fact that you want to be located inside the time like this. So basically then that T star,
Yeah.
the real part of the singularity, that should locate inside the timeline, right? In your real line.
No. Because you see, in that, well, it's, all we know is that the correlator is absolutely analytic inside here. But these guys, R is bigger than 1, are somewhere here.
But you have some special part how your branch cuts start. So I am saying that within those points.
But the branch cut is from here. It's in the OPE part. Right. Because the branch cut is visible in the OPE. I don't need to go to the non-perturbative part to see the OPE. Yeah.
In the boundary in the CFT, the poles of the two-point function of the stress tensor, they somehow correspond to the perturbations in the bulk metric.
Yes.
Now the
Well, they will be corresponding to some kind of quasi-normal modes in the 2 points. Yeah.
But what about the new singularities in the boundary which come from smearing? What do they correspond to?
I'll tell you in a second. Hang on to that question.
So when you compute this CQT from the thing that had omega,
Yeah.
shouldn't sum over omega even integrate Matsushita?
Lorentzian frequency. So I'm solving the Lorentzian wave equation. I'm not solving the Euclidean problem. So the only place I used the Euclidean intuition was to motivate what the OPE would be. But remember when I wrote down the spectral function OPE, the spectral function OPE computed the discontinuity across the cut. Because I need to compute the discontinuity to compute the commutator. Okay, so let me explain where this T star comes from and
One last question.
yeah,
sorry.
yeah.
If I just looked at complex metrics
Yes.
and I just did the beta goes to,
Yeah.
the periodicity. So I get a complex black hole,
Yeah.
but I'm in Lorentzian time.
Yeah.
Will you get the same answer for two-point functions there if you target two-point functions?
I'm going to hazard an answer which says yes
Okay.
for the following reason, that actually to do the WKB analysis we had to allow omega to be complex. So this is an answer obtained.
Somehow I also feel that the answer could be yes.
Yes.
So that is my question then.
Yes.
At that level of differential
This question
equation,
where
these two are
yes.
the same, and
Yes.
where did that get lost?
Yeah.
Fine.
Okay. So let me say something about what is T star and what it had to do with anything I motivated at the beginning. So back in the day, Fitkowski, Hubeni, Kleban and Schenker showed the following. for the Schwarzschild black hole in ADS. They pointed out two things. One was that the Penrose diagram is not a square. The singularity, if you keep the boundary straight, bends down. Two, if you look at space like geodesics that connect the two boundaries, then the space like geodesics tend to be repelled by the singularity. Okay. So imagine fixing Lorentzian time on one boundary and then decreasing Lorentzian time. As you increase the Lorentzian time or decrease, whichever way you go, the space like geodesic at t equals 0 just cuts through the wormhole, just goes straight through. But if you increase the time to lower it to t1, then the geodesic sort of goes up, gets inside the horizon, turns back down and comes back. But surprise, and obvious, if you have already figured out the first part, namely the Penrose diagram is not square, that at some point, okay, this is terrible, but as you ramp down the thing, you will start seeing that the geodesic wants to get closer and closer to the singularity, but after some point, there is no space like geodesic connecting two boundaries.
This is in any dimension?
This is in any dimension. This is an explicit statement for the cleaner black holes. And hang on to 3D. Yeah. Short answer, no, because 3D black hole is orbifold. It knows nothing about Penrose square. Yeah. Okay. And you can ask, what is this critical time? Okay. Beyond which?
The relative time shift.
The relative time shift, yes. That critical time is this time. So they analyze this problem for space like geodesics with zero momentum in the transverse directions. So radial space like geodesics. So increase energy, if you like, of the space like geodesic, the zero energy trajectory goes straight through, but as you increase energy, it sort of looks like this pair of null lines that meet at the singularity. So this has a name, it's called the bouncing null geodesic. It's not a null geodesic, it's not bouncing, but it's what it is.
I'm curious.
How is this time special
From the geometry? From the geometry, it's just a statement about geodesics. Right. So I can ask you a simple question. Pick 2 points on the two boundaries of the eternal black hole. Let them be the same relative time. So time flow is this way. Pick them to have the same relative time, t and t on the other side. Are they not connected by a space like geodesic? Answer is yes, if t is above.
That's not space like geodesic, that's like
So for anything in the epsilon neighborhood of t star, there is a space like geodesic. So it's like saying in the limit t goes to t star, a space like geodesic G generates into a pair of null lines.
And does it not depend on where on these two boundaries each
I took them to be the same spatial point in this discussion because I didn't want to give it momentum. So if we can generalize it to momentum, I'll tell you what happens with momentum, which is related to this statement.
Sorry, you should wrap up, but did you find anything interesting by looking at time like a null geodesics?
No, not in this problem. So there are many caveats, but they wanted to argue following. They wanted to argue that this is a feature that you can ascribe to this two-sided correlator in time domain by saying that this two-sided correlator has time domain singularities when t hits t star.
And that 0 is momentum?
0 is now put, this is x.
Okay.
Okay?
The two operators are the two boundaries.
Are the two boundaries. So I'm trying to imagine that I'm doing some iconal approximation to the 2-point function for large conformal dimension, which I can do. I can imagine that in that iconal approximation, the correlator is dominated by geodesic. The wave equation can be solved by geodesic approximation, and the correlator is given by the length of the spatial length of regularized proper length of the geodesic. Okay. However, this statement has a catch. The catch is simply that this geodesic is not on the path of steepest descent. Okay, so they knew all this. They said all this in their paper, and they said that is a statement that Sandeep was trying to make earlier, that this two-sided correlator has a singularity, but not in the primary sheet. Which is the same statement we are just saying all along, that the two-sided correlator is analytic within the strip because it's governed by the Euclidean 2-point function. So if
Came from where?
they also got it from the Euclidean 2-point function, they just didn't translate it fully into the statement about analyticity in the strip. So the way they said it is that if you look at the geodesic approximation, if you do it as an iconal propagation, then if you're trying to compute the 2-point function, then there is in the Euclidean domain there is a sort of this kind of trajectory, there is this kind of trajectory, there is this kind of trajectory, and these two win over this guy or that guy.
Sorry?
There are 4 geodesics. One is the pairwise things that just go around the thermal circle, the one that wraps around the cigar, and then there is this Lorentzian correlator, and the Euclidean guys win. They are on the path of steepest descent. So a few years later, Hong Liu and Festuccia
Going around the thermal circle on the boundary?
on the boundary effectively. That's the thing that dominates because you do.
That's not infinite length because of the...
No, but this is no, but after
Phenomenon.
renormalization because this is of size beta.
Geodesics never stay on the boundary because
High.
1 by z square.
Well, except at high energies, but yeah, but this is something they made, but this is not germane to what I want to say. So, a few years later, Festuccia and Liu took this statement and translated it into momentum space, and they made the following nice observation. They made the observation that if you look at the quasi-normal mode spectrum, quasi-normal modes come in these families, and this T star is actually associated to the asymptotic direction in the complex frequency space as the quasi-normal modes go to highly damped modes. So if you think of this angle, but only look at it. So high down in the spectrum, Bohr-Sommerfeld is good. Whether it's quasi-normal modes or normal modes, doesn't matter. And that's your statement, that here, they're evenly spaced quasi-normal modes, which are not as even, they won't be evenly spaced up here, but they will get more and more evenly spaced way down in the spectrum. And then you can draw a line and ask what angle does that line make with the horizontal axis. That gives you T star. Okay, so that's how they got this, and they gave very nice arguments, in my opinion, of how to make the iconal approximation precise. But they said it to make the iconal approximation precise, you need the conformal operators to be heavy. You need delta to be large. They also did something also nice, which was to look at what happens when operators are light, but the momenta are light-like. In which case, you have highly ballistic particles, light particles, but moving ultra-relativistically in a thermal medium. Because they're moving ultra-relativistically in a thermal medium, they don't see temperature. They're mostly hovering around the boundary. So those are one case of geodesics which never fall into the bulk.
Shouldn't it be enough for iconal to take high frequency without taking it in?
Correct. So that's what we did. Yes. So this was, we were the first people to read this result in this limit for small dimension was derived by Karan-Ho, Maloney, Joydeep Chakravarti and Afkami Jedi last fall. And there's a related paper by Dordelson, Carlson and Yosa also last fall, just a few months before our paper. And I primarily got inspired by discussing with Simon in their case, because they looked only at zero momentum. So they derived this formula. Okay. Now if you look at this formula and look at our formula, this in 4 dimensions is got pi over 4 is 1, so you get beta over 2. And this hypergeometric collapses. So precisely at v equals 0, you get back the answers that you get for the. So this generalizes, if you like, this formula generalizes this formula by allowing for large spatial momentum. But it limits to the case of spatial momentum correctly. Okay. So I'll say one more statement and then stop.
And just since you introduced momentum, if you did again the two-sided gravity calculation with momentum, you'll see this in the geodesics.
No, this is the problem. Okay. So if you have momentum, then just think of the following simple question or geodesics which carry momentum. Anytime you have momentum, whether it's spatial or angular, you have a centrifugal barrier, which means the effective potential is something like this. It's area, so it goes up. So you are prevented from bouncing off the singularity. Nevertheless, the correlator knows about this. And for me, the $1 million question is there a direct connection apart from the sort of circumstantial evidence that says, look, you can see the same temporal dependence showing up in multiple places between the Lorentzian bouncing geodesic, if you want to call it that, versus a sharp statement about asymptotics of spectral functions. Okay. So the current observation that various people have made is that if you look at the singularities in the complex plane outside the fundamental strip, locations of the singularities have some avatars, should be thought of as imprints of the black hole singularity. There's been one set of calculations that I described, which are all purely bulk, where you sort of use the bulk to derive these guys. There's another set of calculations which I recommend looking at, which I won't describe in detail, by Matthew Dordelson initially, and then by Dordelson, Iosa, and Carlson from last fall, where they looked at something simple like SYK model. And in the SYK model, in the strong coupling limit, you don't see bouncing singularities because the strong coupling limit is governed by some silly conformal ADS2 theory. But you can ask what happens in perturbation theory. So small beta, small coupling for the SYK model. And you do see this quasi-normal type structure. This is what Matthew did initially. And you also see, if you translate it to intermediate couplings, something like what you might want to call some alpha prime resolved singularity structure. Okay. Take it with a grain of salt because it's not really clear in that case whether there's a holographic dual. But I think that example to me shows some promise that if you could make this statement sharp, and if you can develop, if maybe not in n equals 4, but in simpler matrix models, some form of matrix model thermal bootstrap, which already exists so there's a nice paper by Minjae Chow, Ji Yin and friends from last fall, where they can actually compute 2-point functions simply by using positivity constraints in large n matrix models. One could ask, do these large n matrix models, which have all the features, 2 matrix models, some people here well know, have all the features that you expect in holographic systems? Can we make this statement sharp? Okay. I'll stop there.
Sorry, I didn't fully understand the statement with momentum. So with momentum, that form is different. This was for q equal to 0.
Yeah.
But there is, what is the analog of P star then? It's that entire correction series.
No, it's yeah.
And then, so I mean, I'm just.
It's shifted by this new parameter.
Right?
It's shifted by this v parameter.
But I'm just saying here for q equal to 0, there was this real part which was independent of, I see, actually even there, the u,
Yeah.
u part, because u is something what is it,
You use some integer.
is some various integers. Huh?
Yeah. Some
So
z mod something.
Even for q equal to 0, there is some, you have some multiple bounds in geodesics.
Yes. Because they come from multi-instance. Each geodesic is like an instance. So.
And then for q not equal to 0, you have the real part, which is the analog here.
Yeah.
So u was also the dimension.
No.
U was this. And we seek a geometric, in a sense, interpretation of that. Is that true?
Yeah. I can tell you what it is. It's a period integral, but yeah. So it's a WKB
That's
period
a
integral.
I mean, in the bulk, in terms of geodesics,
Yes.
one doesn't know.
Yeah. I don't have an immediate interpretation, but
But there's some geodesic which is probably spinning.
it's some complex geodesic, so it's not real geodesic. So. But it's not on. I'm pretty sure it's not on the real Lorentzian section. Okay.
Is there some sense in which the singularity comes from like the complex R plane
Yeah.
from the inside of the disk or something? I know that it's not so.
Actually, yes.
Okay.
For the following reason, it's a statement I made about monodromy. The monodromy between horizon and infinity is the same as a monodromy between singularity and every other horizon.
Okay.
So, in fact, the cheapest way to compute this is to compute that monodromy.
But actually, I was thinking that because the monodromy was between R plus and infinity,
Yeah.
in a sense, it only knew about the geometry outside.
But that's what I'm saying. But the net monodromy, I can flip it around. The trace is the same. It's the same trace.
There's nothing in there, Victor, or there is nothing on the physical, in terms of physical operators that you see.
No, there is no local statement, which I think is.
But you need something, I mean, no actual observable you can compute. No experiment you can do with having a two-sided geometry, which would detect the signal.
You're saying, what is this analytic configuration?
Yeah. That I agree.
Yeah, is it expected to be some funny contour?
I don't know. I wish I knew, but it sounds like it. But you know,
Funny contour, I mean, some sheet or something.
I mean,
he means something more like some deformed Schwinger-Keldysh contour that goes somewhere.
You know,
Yeah.
correlation functions have many sheets.
Yeah.
And some of these sheets can be interpreted as going to different
So,
concepts.
yes.
That would mean some out of time kind
Something.
of generalized correlator.
Something
right?
like that. Yeah, that would be very satisfying. That is very physical.
Yeah. But this is a 2-point function, Shira. So
I know. There's very
it's
different things you can do, right?
It's nothing out of time ordered.
Yeah, I know.
It's either or odd order. That's it. In fact, they're related. So in this case, it's just one of them. So.
just to understand, like this calculation was done using velocity, right? But
Yeah.
if I had access to the exact one of system and
Yeah,
I did this
yeah,
calculation,
yeah.
would I expect to find something periodic, which this function is not?
Actually, this is a nice part. This is where it's worth understanding this. So, Matthew's calculation in the perturbative SYK is definitely not periodic.
Not periodic.
Not periodic.
But that's an exact calculation?
It's an exact. Well, the way he did it, I can tell you how he did it. He used Altman and friends operator growth story and computed moments. He actually just directly computed moments of the 2-point function in time domain to very high order. But they approximated it on the poles.
But that's not exactly. It's still large n, right?
It's larger end, yes. It's larger end, but you can either do it for sufficiently large n, or you can just take the Schwinger-Dyson equations and solve them.
Right, so you're saying that actually the exact correlator will also not be periodic because why?
Why should it be?
But at least it won't be singular, maybe the singularity will be singular.
So that's expectation that somehow they will get smeared out or get they get. That was their statement in the recent paper that they get they start slightly broadening into cuts as you go to finite coupling, but no statement at finite end so far.
It's very hard to know, because with the higher point correlators, there is some Schwinger-Keldysh continuity. There's so much more stuff.
I think it's not going to tell you any more, because I'm pretty sure the analytic structure in momentum space of higher point functions is the same as what is in 2-point functions.
What is it?
2-point functions. We sort of proved this in many examples with Loga, so I think this is true.
You have so many more choices.
Doesn't matter. I think all the Schwinger-Keldysh higher point functions are completely governed by quasi-normal nodes.
Even at zero temperature, if you take 4-point functions,
Yeah,
there's an infinite number of sheets.
yeah.
And some of them you can interpret as various orderings.
Orderings.
But most you can
Yes.
have not yet.
Yes.
This is that kind of question. There are
Yeah.
some sheets.
Yeah.
One more question about
Yeah.
this formula I find very interesting.
Yeah.
It seems to give you some structure for the failure of the OP, if that's the right way.
That's one way to think about it. At least for these dimensions, I think yes.
Okay. I was wondering if you could now that you know the formulas, sort of understand it. It's a big question. From the OP and failure.
Yeah.
I mean, getting OP to work in momentum space is a very interesting thing.
Yes.
And you seem to have some control over how it works, if that's the right way of thinking of it. And if one could sort of get a first principle expectation of this, it might generalize well beyond.
Yeah, no, I agree. In fact, it would be helpful even for the sort of more pragmatic question of making these statements sharper for these non-integer dimensions where we had control. But yes, we can chat about it. I don't have a immediate answer to offer.
How generic are these bounds in geodesics or in Dyson and Nordstrom, for example? Is there anything of this kind?
Okay, I didn't want to talk about it, but since you asked. So clearly space like geodesics don't bounce off National Nordstrom.
Yeah.
Right? Because the geodesic, the singularity is to your future.
Yeah. I was wondering if you see the inner horizon or something.
So if you do space like geodesic, they will get stuck well below the Cauchy horizon. They will bounce somewhere, they'll never penetrate past the Cauchy horizon.
But they still have this bouncing kind of feature.
They still have some kind of bounce. So in fact, it's not dissimilar to the attractor solution of Mulder-Sena-Hartmann for the entanglement entropy in short shell, blah, blah. But time-like singularities do bounce of the time-like geodesics do bounce of the time-like singularity. Except that they are between one boundary and another boundary to the future. Okay? So in a paper from also last fall, Hong, Parnachev and friends argued that this technology, their technology of this OPE statement I was telling you about, adapted to charged black holes, manages to see that bounce, and they predicted some statement of this kind for the location of those bouncing singularities. Now, what those observables are, your guess is as good as mine. What 2-point function is being computed, I don't know. Should that be a well-defined field theory observable, then yes.
And there are these arguments about how the region is unspherical because
Yeah.
the inner horizon
Yes,
case of
yes.
everything.
But you see, this is a probe calculation. So to see the inner horizon instability, you'll have to backreact. Yeah, which we are not doing here. Yeah, that. Yeah. But I thought that they just studied the geodesic analytic structure of geodesics and not particularly the singularity, whereas these guys actually showed where the singularity was.
There was this paper sometime 2-3 years ago by Geodesics and friends doing something interesting about two-sided correlators.
Yes, the thermal product formula paper.
Yeah.
Yeah.
I haven't internalized that. But
Yes, actually, the formula I erased in terms of gamma functions, you can repurpose it into the thermal product formula.
so that formula was somehow, was it writing these 2-point functions in terms of quasi-normal mode folds?
Yes.
Sort of like a generalization of the Hartnell and such kind of thing,
Correct.
but for two-point function.
Correct.
And so that only knew about the quasi-normal modes.
Agreed.
But you see these extra singularities also.
Yes, yes. If you look at the asymptotics of the quasi-normal modes, then you immediately see the singularities.
I see.
So if you start with their formula, do the asymptotic analysis, you will get that answer.
And the other thing about that formula that sounded really interesting was that the residues
Are simple,
are very simple.
very simple. Yeah. But again, here the fact that in this gamma function ratio,
Yes.
there was some simple factor. So something magic happens. Yeah. So, I mean, they argued for it from this, analytic structure, some complex analysis. They didn't really, they derived it from that logic. I'm pretty sure it can be derived from this Virasoro block, but it's almost the same thing. But